Hi, I'm Ryan Nickel, CTO at DSA Ocean, and today we're going to talk more on how to calculate the radiation and diffraction coefficients for a simple box barge. So where we left off last time was we drew this 20 meter by 20 meter by 2 meter tall box in Rhino, exported it to OBJ, and then brought it into the Shipmo 3D toolset. So here you can see the mesh. Now, there's a few more steps you have to go through before you can get to the radiation and diffraction calculation process, so we'll go through those now. The next application is optional, but I do recommend you do it. This panel lid application here. So we merely have to select the wet hull that we generated in panel hull. And there's a few methods to calculate the lid for this, but usually it works pretty well. And what's happening here is, if we go to plot panel lid, what this is doing is generating a numerical lid that fits inside of the hull mesh. And what this is useful for is part of a numerical process that suppresses any wave effects that show up accidentally inside of the hull. So it's purely optional. It's purely a process for increasing quality of hydrodynamics calculations in the RadDiff process, but it's really quick and easy to do, and I definitely recommend you do it. Just be careful. You just take a quick look at it and make sure that it's fitting inside the wetted hull area for multi-hulls or individual monohulls, that sort of thing. Okay, the next step is now we want to go to add new data and select RadDiff. So here we select the wet panel hull file. Again, that was generated in panel hull, and we have the lid file. We just created that in panel lid. And there's a few options here. Very generally, mostly the default parameters for these are all fine. The most important thing to do, I always recommend you uncheck include diffraction calculations first to make sure and focus on the radiation calculations. The reason for this is that you want to make sure you have enough radiation frequencies first. These calculations take an order of magnitude less time than all of the diffraction calculations, and it's purely just because there's more cases to check, and I'll expand on that in a moment. But we want to make sure we have an adequate number of encounter frequencies, encounter frequency range here to capture the variation in the wave radiation parameters, and we'll see that in a moment. Now I've taken a look at this already, so I know that this should look like a pretty good range. What I'm going to do is just put in 0.05 here. I recommend you do something a little bit more coarse and do a quick, at least one run to just see what happens first, especially if you don't have any experience with the hull, and then include the diffraction calculations. So these are doing all the wave radiation calculations. In other words, as the hull moves, what are the forces generated from the radiating waves away from the body at a range of different frequencies. And then in the diffraction calculations, the hull is fixed, and there are incident waves coming along and diffracting around the hull and creating new forces and wave excitation forces. And the reason it takes so much longer than the wave radiation forces is just because there's so many more cases to look at. There's different forward speeds to consider, and there's different directions that the waves come relative to the hull, and also a set of wave frequencies as well. And these frequency ranges you should make sure you capture enough that you'd expect to see in some incident C state. So again, a lot of these defaults are okay. It kind of depends on the forward speed parameter that you're using. Barge is not high speed, but I just put in larger numbers to encompass that. So note optional parallel processing here that definitely helps with the computational effort too. So we'll run this, and the calculations really depend on the number of panels you have and the number of cases that you've selected, the number of frequencies. Usually it's going to take at least an hour or so for all these calculations to complete. All right, so we'll let that run, and we'll check on it shortly. Okay, some time has passed, and now we want to check out the results of the calculation. So if we look at plot radco, what we can see here is a encounter frequency variation of the wave radiation parameters, the added mass and damping values. These are for surge motion, sway motion, heave, roll, pitch, and yaw. These last two, longitudinal and lateral condition numbers, are purely numerical conditioning numbers, and very generally these are excellent, very low values, on the order of 10,000, and so conditioning numbers that are on the order of 1e to the 5, 1e to the 6 are potentially signaling there may be some irregular frequencies in the results, but those are only usually a concern if you happen to see any noise or fluctuations, sharp fluctuations in the frequency-dependent added mass and damping. Very generally, what you want to see for damping values is at low frequency or zero frequency, the damping values are 0, and at infinite frequency or the highest frequencies, you've got them back down to 0 again, and for all degrees of freedom. For most types of ship hull, you'll see some kind of single hump and some smooth variation. You can see some ripples here in yaw. It's kind of normal. It just sort of depends on the degree of freedom you're looking at and how much of a strong the wave effects are in those conditions. So as I think you might imagine, yaw motion is for a box barge would be a little bit more funny and not as strong as something like in heave motion, where it's an excellent wave maker. Now, in contrast, the added mass values, at low frequency, they converge to some constant value, some non-zero. It may be 0, but it's usually non-zero value. And then at high frequency, they converge to some other different value. And very generally, that's kind of what we're seeing. I mean, it's not exactly perfectly converged here, but it's looking pretty good, especially after a long range of frequencies where not much is happening. And again, generally it's looking pretty good across the different frequencies. So I'd be happy with these results. And we go back to rad diff, and there's more details you can see in the output if you want to. But we'll continue now with constructing the rest of the model of the ship. So we use another application, add new data, and we go to build ship. And what we do here with build ship is select the wave radiation and diffraction database we've computed, the dry panel that was calculated in panel hull. Here's your option for providing the roll, pitch, and yaw radius of gyration, though you only need those values if you're going to continue on to calculate motion and do the seakeeping and maneuvering analysis within the Shipmo 3D toolset. What we're going to do is actually export the hydrodynamic data from here and bring it into a ProteusDS project and show you more about how to work with projects that way. We do want to look at some of these parameters for evaluation of the hull retardation functions, also referred to as kernel functions. And we'll look at those in a moment. There is a resistance curve that you can specify as well. This is wave making and viscous resistance. Halltrop-Menin is a great method that automatically provides a resistance curve based on some parameters on the ship length and so on. The only challenge is that it will break down at very squat and very low length to beam ratios of vessels, and in fact I think that's what will happen here, and we'll look at that in a moment. You can also, again, if you're continuing on to do ship motion analysis in the Shipmo 3D toolset, there's lots of great options here for hull appendages that you can include, like skegs and bilge keels. Yeah, but we'll look at that in other video tutorials. So we'll click run for the moment, and I believe we'll see an error. If you look at the error log, you'll see a reference to Halltrop-Menin. The workaround for this is that you can provide custom resistance coefficients accordingly. So we'll hit run. Now you do need to run this to also plot the kernel functions. Now these kernel functions are part of the numerical translation process to take frequency-dependent added mass or added mass and damping information from the wave radiation effects and incorporate them into time domain, which you will need for maneuvering, but also for work in the ProteusDS simulation toolbox work too. So if we go down and go to plot retard, the plot retardation functions here what you'll see is generally these functions that look like they're decaying to some 0 value, and generally that's what you have control over, is the amount of time that these functions go on. So I think this is 8.5 seconds. You would just double check that. Here, yes, the maximum time is 8.5 seconds. You want to make sure you have enough time that these have a chance to fully decay down to 0. And this is the function for surge, for sway, for heave, and then the rotations here as well. And so generally, these functions, these kernel functions, are part of the process of, again, translating frequency-dependent information into the equivalent time domain value, and they're applied on the velocity history. Interestingly, you'll see in red forward speed-dependent terms on the kernel functions, and you can see that sway has some interesting parameters here, but it's not as strong in the other degrees of freedom. So once you've checked that, again, just making sure you've got enough resolution in here to capture the details and also enough length. The other thing you need to do is make sure you have checked export ProteusDS radiation and diffraction terms, and we'll run that again. And now when we look at our project folder, it's usually a very large, much larger file than the other ones. Here we have the square barge ProteusDS radco file. And if we take a look at this, you can see essentially what this is there's a huge lookup table with a lot of frequency-dependent added mass and damping information, the kernel functions, as well as there are the kernel functions there, as well as a lookup table for the incident and diffracted loads at a range of speeds and frequencies and directions. So in the next video, I'll show you how to import that into a ProteusDS simulation toolbox project. Thanks for watching.